Swayam Prabha. Digital India. Educated India.
Welcome. So, we were discussing about the 10 assumptions of classical linear regression model, assumptions of CLRM yesterday we were discussing. So, this is basically assumptions of CLRM that we were discussing yesterday. And once again I would like to repeat that these assumptions are required. Why? Because these assumptions they describe an idealistic situation under which the CLRM estimates they exhibit the three desirable properties. So, if these assumptions are maintained and then we estimate the model, so our estimates of alpha hat and beta hat will exhibit the desirable properties of efficiency, unbiasedness and consistency. So, yesterday what are the assumptions we discussed? Firstly, we said that the model is linear, and when I said linear, it is linear in parameter. Then we have also discussed that the error term, this is our model, right, yi equals to alpha plus beta xi plus ui. Then we said that the error term, mean of the error term, expectation of ui given xi equals to 0, and error term does not have any covariance with the explanatory variable. So, that means covariance between xi and ui equals to 0, and when this assumption is maintained, then we said that basically xi's are exogenous, okay, in the sample. That means xi's are fixed over repeated sampling. Then we have also discussed that there should be enough variation in your independent variable xi so as to include this xi in our model as explanatory variable. If there is no variation in xi, then xi does not qualify to be included as an explanatory variable in our model, right. And then today what we will do, we will discuss about another assumption which says that number of parameters to be estimated in the model, which says number of parameters to be estimated let us say that we are trying to estimate k number of parameters from the model. So, number of parameters to be estimated from the model should be much less than total number of observations in the sample. Which is, let us say, n. Alternatively, we can say that number of observations in your sample should be much greater than the number of parameters to be estimated in the model. So, we can say that n should be much greater than k. For example, in this model how many parameters we are going to estimate? We are going to estimate only 2 parameters, alpha and beta, so k equals to 2. So, what should be the exact number of observations? There is no clear cut rule set by the econometrician, but as a rule of thumb we can say that it should be 20 times larger. So, minimum 20 times larger than the number of parameters. So, if you are estimating 2 parameters, then probably you should get minimum 40 observations, and more is better, more is always better, right. This is the assumption. So, if you try to estimate 2 parameters and your total number of observation is, let us say, 5. So, that means in that sample estimate of alpha and beta would be unreliable. So, we cannot rely much on the alpha and beta estimated from a very small sample where number of observation is just greater than the number of parameters. So, n should be much greater than k, right. And then assumption number 6, it say that the model should be, the econometric model should be correctly specified. Okay. That means there should not be any model misspecification. Okay, model misspecification. Now, model misspecification is also a serious problem in econometric analysis. Sometimes econometricians, they say that model misspecification is basically as dangerous, is so dangerous that they term this model misspecification as keys of death. What I am saying? Keys of death. So, model misspecification is known as keys of death. Keys of death. What does it mean? Keys of death indicates that model misspecification problem is so subtle in nature, you won't even realize that you have made the mistake, you have misspecified your model, but the consequence is so severe. Okay? Since it is very difficult to identify that you have committed the mistake of model misspecification, but the consequence is highly dangerous. Okay? Consequence of model misspecification is so severe. That is the reason they say that it is basically keys of death in econometric analysis. So, we should first ensure that our model is correctly specified before we actually estimate the model using data and all. Now, there could be two types of model misspecification. Okay? So, you can commit basically two types of model misspecification. Model misspecification could be of two types. Could be of two types. Number one, due to improper functional form. Due to improper functional form. This is the first type of model misspecification. For example, let us say that our true model is this: yi equals to alpha plus beta 1 x 1 I plus beta 2 x 1 I square plus ui. Okay. Now, what type of model we are specifying here? This model you can think of a cost function, okay, a marginal cost function, where in the x axis we are measuring output, which is denoted by x, xi is output and this is cost. And as you all know, let us say that I am interested in estimating a marginal cost function, which is an U-shaped relationship between cost and this is our yi, this is basically yi and this is output. So, that means we know that the relationship between yi and xi is nonlinear and it is ui. So, as production increases, marginal cost comes down initially and then it goes up, right, U-shaped relationship. And that U-shaped relationship, if you want to estimate, then you need to specify this type of model, yi equals to alpha plus beta 1 x 1 I plus beta 1 x 1 I square, right, square. So, it is coming from our standard quadratic equation form, which says that ax square plus bx plus c is basically ax square plus bx plus c is the standard form of a quadratic equation. Same quadratic equation we are imposing here, and this is our cost function, true cost function. But by mistake, let us say that you are specifying this type of model, yi equals to alpha plus beta 1 x 1 I plus ui. So, that means when the true relationship is nonlinear, you are specifying a linear relationship like this. Okay. So, what will happen? That means if you specify a linear relationship, then actually what you are doing, you are either overestimating or underestimating the cost of production. For example, let us say this is point A and this is point B. So, at the left side of A, your true cost is actually higher than what you have predicted through this linear function, and beyond B, your true cost is actually, your predicted cost is actually lower than your true cost. Okay. So, and in between A and B, what is happening? Your true cost is actually lower than the predicted one. So, that means your model is basically overestimating. Okay. Your model is, there is a problem of overestimation in between A and B, because this is the line you have fitted where the true relationship is this, and beyond B it is again, it is underestimating, and left side of A also it is underestimating the cost. So, in between A and B, this is overestimation. 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 Right. So, this is one type of model misspecification arising due to improper functional form, where my functional form says my variable should appear in the equation in its level form as well as in its quadratic form. So, that means when the functional form requires nonlinearity in variable, you are specifying a linear relationship between yi and xi. That is why you are either overestimating or underestimating the cost. This is model misspecification due to improper functional form. Secondly, model misspecification may also arise due to inclusion of an irrelevant variable irrelevant variable or exclusion of a relevant one. So, from this example itself we can understand that here what is happening, your true model requires x1I square also to be included, but you are excluding it when you are estimating. So, you are specifying this equation yi equals to alpha plus beta 1 x1I. So, that means x1I square is omitted. Or you can think of a completely different example. Let us say that your true model is yi equals to alpha plus beta 1 x1I plus ui. This is your true relationship, but unnecessarily you are estimating this type of relationship yi equals to alpha plus beta 1 x1I plus beta 2 x2I plus ui. This is incorrect, as x2I does not have any impact on yi. Okay, this may happen. So, this is basically inclusion of an irrelevant variable. Similarly, it may also happen that if your yi equals to, let us say, lambda 0 plus lambda 1 x1I plus lambda 2 x2I plus epsilon I. Let us say this is my true model, but you are specifying this yi equals to lambda 0 plus lambda 1 x1I plus epsilon I. This is incorrect because you are omitting an relevant variable x2I from the model. So, these two examples they say that these are the two types by which model misspecification may arise, either due to improper functional form or due to inclusion of an irrelevant variable or exclusion of a relevant one. Okay? This is assumption number 5. Then assumption number 6. Assumption number 6, it says that the error variance is constant. The error variance is constant. That means in your model, when you are specifying yi equals to alpha plus beta xi plus ui, that means you are saying variance of ui equals to sigma square. Variance of ui equals to sigma square. So, that means what is I? I is basically the I is indexed for individual. I is indexed for individual. So, that means the variance of the ith individual's error term, this is the equation I have written, I have specified for the ith individual. Similarly, you can write another equation for the jth individual, yj equals to alpha plus beta xj plus uj, and variance of ui, uj, uk everywhere it is sigma square. That is why there is no I subscript over here. Okay? The error variance is constant, and if that is the case, this indicates a situation of homoscedasticity. Homoscedasticity. Okay? Alright. So, what does it mean? In a simple diagram, I can make you understand this situation. Let us say this is xi, your income, this is yi your consumption, and let us say this is your line that you have specified, yi hat equals to alpha hat plus beta hat xi. Okay. So, for any level of xi, let us say this is x1i, you will have point like this. That means, while your line predicts that the predicted income should be here, your actual predicted consumption should be here, but if you look at your data set, you see that your actual consumption is either above the predicted line or below the predicted line. So, that means either you have made positive error term or negative error term. Okay. So, positive error term or negative error term, and these you can think of the spread of the error term. Similarly, this is for x1, x2i. Similarly, for x3i, this is for x3i. So, from this diagram you can understand the spread of the error term, the spread, this is called the spread or variance of the error term is actually same. Okay? Variance is same. When your income is increasing from x1 to x2, x2 to x3 at higher level of income also, what I see as x changes, okay, different individuals will have different income, but the error variance is constant. That is what we assume. This is called constant error variance or homoscedasticity. Okay? Constant error variance or homoscedasticity. But in reality, we may or may not have this type of situation. We may get a situation where your error term becomes heteroscedastic in nature. Actually, that is the realistic situation. What is the reason for heteroscedasticity? What is its remedial measures? And how to detect this heteroscedasticity problem, that we will discuss in detail later on when we come back to this particular chapter called heteroscedasticity. That means, later on we will try to relax this assumption one by one, and we will discuss their detection, remedial measures and consequences. So, for the timing you just understand this is the simple meaning of heteroscedasticity. That means, at different level of income, the variance of the error term is actually constant. There is no change in the spread of this error term, right. Then the assumption number 7, it says, assumption number 7, it says that there should not be autocorrelation. Autocorrelation. What does it mean? Once again, it says that when your model is yi equals to alpha plus beta xi plus ui. So, let us say this is yi equals to alpha plus beta xi plus ui, the equation I have written for the ith individual, and then it is the equation for the jth individual, then alpha plus beta xj plus let us say uj. Then the autocorrelation, this particular assumption, they say that covariance between ui and uj is actually 0. Now, though this term is actually covariance between ui and uj, it reflects the correlation between ui and uj. This is actually not autocorrelation, this is known as spatial correlation. Spatial correlation. And if you are dealing with a time series data, then you will have this type of situation, ut and ut plus 1 or minus 1, should also be 0. So, if this is not 0, then only it is called spatial correlation, and this is called autocorrelation. Autocorrelation or serial correlation. Serial correlation. Why this is so? Because so that means this is called spatial or autocorrelation, but our assumption says that there should not be this type of relationship. So, presence of either autocorrelation or spatial correlation is eliminated, is ruled out by the assumption so as to so that our estimates of alpha hat and beta hat shows the desirable properties. Now, why does this autocorrelation, spatial correlation or autocorrelation problem arises? So, when you are dealing with cross sectional data, so that means let us say this is your yi consumption is a function of income plus ui, and this ui basically captures the omitted variable, as we mentioned, the omitted variable which might also have some impact on yi apart from your income. Now, when you are collecting data, then it may so happen that let us say the ith individual and the jth individual, they are residing in a same place. So, that means ith individual and jth individual's consumption might be influenced by some other factor which is not there, and let us say that is basically weather, you have not included, that is why it is there in the error term. Since ith and jth individual, they both are facing same type of weather, just because they reside in a same place, it might so happen that ui and uj, they are correlated. Okay. So, this is the problem in cross sectional data, and this is the reason for spatial correlation. Since the two individuals are residing in the same place, their consumption pattern might be influenced by a same variable which is not included in our model. Okay. And if it is weather, for example, then ith and jth individuals' consumption are influenced by same type of weather. It might also happen that ith and jth individuals' taste and preference is also same, since they are residing in a neighborhood. In that case also there is a possibility that ui and uj will be correlated. All right. And then when you are dealing with time series data, then what may happen, your equation would be yt equals to alpha plus beta xt plus let us say ut. All right. So, what happens when you deal with time series data? Sometimes our variable, let us say this is your GDP and this is your employment data. So, many times these type of macroeconomic variables, they get some kind of external shock. For example, what type of shock? Let us say financial crisis in 2008. Financial crisis in 2008 or the recent COVID-19 pandemic. So, these external shocks are given in the economic system. Then what happens? The impact of this shock does not die down immediately. That means the impact persists in the system for some time. Now, what happens? Since this shock you cannot actually observe, this error term captures actually the impact of these external shocks which is given in the economy. So, starting from 2008 onwards, 2009, 10, 11 and all other years, your variable, the error term, will get impacted by the same type of shock which was given earlier. Since the error term is influenced by same type of shock, it is quite likely that they get correlated in a time series data. Okay? These things will become much more clear. Let us say this is your xt and this is your yt. So, what happens that when external shock is given, your time series macroeconomic variable, let us say this is let us say this is your equation, or in terms of this is, let us say it is time. Okay. So, your time series macroeconomic variable will show some kind of pattern like this. Let us say this is your yt. So, this pattern is actually known as business cycle in macroeconomic literature. So, due to external shock, when the economy is going down, that means when the economy goes for recession, that means what is happening? In each successive period, GDP of the country becomes lower than the previous period. So, that means yt is greater than yt plus 1 and yt plus 1 is greater than yt plus 2, like this. Or when it is going up, then the reverse pattern will observe, then again the pattern like this. Okay. So, when in each successive period your yt shows a pattern, yt greater than yt plus 1 and yt plus 1 greater than ut plus 2, yt plus 2 is greater than yt plus 3. Obviously, from these what we can write, yt plus 1 would be alpha plus beta xt plus 1 plus ut plus 1, right, and then yt plus 2 equals to alpha plus beta xt plus 2 plus ut plus 2. Since yt plus 1 and yt plus 2, they show some kind of pattern, what we will observe that ut plus 1 and ut plus 2 will also show the similar type of pattern, and because of which we will end up with this type of autocorrelation problem. Okay? This is the reason. Of course, we will discuss again in detail about the autocorrelation problem, basically how to detect autocorrelation problem, what are the other reasons of autocorrelation problem, and how to solve autocorrelation problem in a later part of our discussion when we will come back in detail with autocorrelation.